Let's look at one last idea now that's based on ocean pH. So we have to go for that to the calcium carbonate equation. So here K prime Sp, which should be a subscript here, is an apparent equilibrium called solubility product. So you have, when you split calcium carbonate, you get Ca2 plus and CO3 minus minus, obviously. And the calcium carbonate in the ocean has two crystal forms. One is called aragonite, one is called calcite. Aragonite is much more soluble, which means it cannot be found at greater depths. It gets dissolved with the acidic water, so it only gets deposited in shallow depths. And the other thing is the carbonate ion, CO3 minus minus. If you look at micromole per kilogram, it's actually like a mirror image of CO2. CO2 was low at the surface, increased, and then remained almost constant with depth, with the respiration, remineralization of the organic matter, and other animals living in the deeper waters, and so on and so forth. So you can see here that the carbonate ion has higher concentration near the surface, decreases down to about 1 kilometer, and then essentially becomes almost constant. So if you look at the saturation levels of calcite, so saturation concentration of calcite with depth is down here, and the aragonite, which is much more soluble, obviously has much higher levels of saturation. So by the time you reach a depth of about 3 kilometers, you are already way below the saturation level of aragonite, so it's much more soluble. This is for the South Atlantic at 20 south and 25 west. This is at the for the North Pacific at 42 north and 152 degree west. And you already remember that the CO2 in the Pacific Ocean is much higher, so pH is much lower. So you see the corresponding differences in calcium carbonate and carbonate ions as well. Much lower surface supersaturated levels. It has to be supersaturated at the surface because the calcifiers, like coccolith, force forams coral reefs. Well, at these latitudes you don't have coral reefs, but nonetheless you need supersaturation, and then drops off again and nearly constant, and you can see the saturation of aragonite and calcite here. So coming to the idea of pH controls on glacial CO2, obviously if CO2 drawdown into the ocean increased, then pH would have been much lower. You can see the impact of calcite saturation in terms of the depths here. So where there is lower CO2 and higher pH, you have sorry, let's make sure. Yeah, so you have deeper calcite saturation depth in the Atlantic, except the mid-ocean ridge, which so clearly shows up here because that's shallower, where you have huge calcite depositions because it's way above the saturation depth. But if you go to the North Pacific, you have much shallower calcite saturation because the waters are much more acidic. So that's just kind of a consistency check with what we are talking about. But in terms of the story of how pH control should work in the glacial times, we have to again come back to a few consistency checks. The pH would have to have been much higher if you were to rain out much more calcium carbonate, because if you reduce pH, you're going to dissolve calcium carbonate and you're going to reduce deposition. There is some evidence that there was increased deposition of calcium carbonate during the ice ages. This could have happened in many ways. One of the arguments is that the glaciation would lock up a lot of the water on land, so sea levels would be lower, so the shallower shelf areas would have been exposed to weathering. So you would weather a lot more calcium carbonate from land, bring it into the ocean, but there is no evidence that weathering was that much higher. Especially Ice Age would have had much lower temperatures, and we know that lower temperatures means lower weathering rates. And in the ocean, if you rained out a lot of calcium carbonate, then we know that the calcium carbonate pH stat would begin to act, and then that would require a balance of calcium carbonate, so you would not be able to deposit too much excess calcium carbonate without having either compensating inflow. People argue that maybe coral reef hypothesis worked, where coral reefs were somehow depositing more calcium carbonate instead of coming from weathering. I hope I made that argument properly, but please read the book for better explanations. The other argument goes back to the silica, where we know that when there is more silica available, diatoms compete much more than the calcifiers, and diatoms take up silica and nutrients, and having fewer calcifiers would draw down the CO2 from the ocean, from the atmosphere into the ocean. But this also doesn't give us enough of a drawdown. We want still 80 to 100 ppm. All these ideas of ocean pH changes and calcium carbonate pH stat working together does not give us still enough drawdown of CO2 of 80 to 100 ppm. Okay, so the long story short, the ocean pH changes are not large enough based on the evidences, and the calcium carbonate depositions are not large enough to explain the pH changes driving increased or increased drawdown of CO2 into the ocean, right? So again, we are back to zero, saying that each of the ideas has merit in terms of explaining the CO2 change in the right direction of reducing CO2 during Ice Age, but none of them give us a total of 80 to 100 ppm. Okay, so we talked about circulation changes, we talked about biological pump, we talked about increased dissolution because of colder temperatures, and we talked about pH changes. None of them give by themselves enough of glacial deglacial CO2 change. So that leaves us having to wonder about what would happen with global warming. Under global warming, essentially we are talking about all sorts of feedbacks. So climate change is happening because of increased atmospheric greenhouse gases. So we have radiative forcing, and then ocean solubility, CO2 solubility in the ocean is driving lots of changes. Ocean acidification is one of them, stratification change, productivity change, and the carbon uptake change are among those things. There is the CO2 fertilization effect on land, where vegetation which depends on CO2 levels in the atmosphere for photosynthesis, if CO2 increases, the stomatal conductance changes, and the stomata doesn't have to remain open as long because CO2 is higher. You know, stomata opens to take up CO2 without losing too much water vapor. So increased CO2 can have a what is called a CO2 fertilization effect. Again, there is some evidence. And climate change increases respiration because warmer temperatures increase the respiration of organic carbon and so on. So all these feedbacks will happen, but the story of the glacial change that we are trying to explain with various hypotheses, and none of them worked completely, means we are basically facing somewhat of an uncertainty in exactly what the carbon cycle response is going to be as far as the ocean changes and ocean drawdown of CO2 and the overall balance of CO2 as we keep increasing emissions. There are many other ways it is said. People keep looking specifically at the Southern Ocean, for example, which is a very big carbon sink, and with the warming and wind changes and the movement of the subtropical front and so on, is the carbon uptake in the Southern Ocean continuing at the same rate or not, and whether the stratification changes, for example, warming the surface makes the ocean more strongly stratified. There is some evidence that this drives down primary production because mixing up nutrients is harder, and whether that is reducing carbon uptake as well, and what's happening to the export of carbon from the surface and so on. So essentially we have positive feedback of the carbon cycle at Ice Age timescales, but how this corresponds to the global warming situation is not entirely clear at this point. But we will go forward and look at other issues associated with the global carbon cycle in the context of global warming.